his
That is a
work,
DFA.
yeah, that he has worked in, he's in applied mathematics at, I guess, at Porto University, am I right?
Yes, yes, you are
And
right.
you work mostly on kind of entropy measures to financial time series,
Exactly.
the
Agent-based
connotation.
models, for example. I teach in an economic school, so
Yeah. So this very, I mean, I'm sure you are probably friends with Gene Stanley, who is here in Boston.
yes, yes.
We
I
all,
met Gene several times since the early 2000s.
yeah, we always have him at the regional meeting here at this section of the Complex Systems Society
Mhm.
in Northeast United States, basically, to
Okay.
speak. But yeah, I think yeah the time is
Okay.
my
I
watch
can start
12:45.
when you
So
want
let's
to.
start.
Okay, thank you. So my purpose today is to present you about XDFA, that is a software to evaluate the detrended fluctuation analysis. The basic outline, I will do some kind of introduction. I will say briefly what is the Hurst exponent, and I will discuss some of the implementation issues, both in terms of the computer and the challenges to implement software. Because for most of us, software is natural, but one of my interests is also scientific computing, and I think that if we do computing, we should do it well. That's it. And the output of my work is the XDFA, and you will understand why the X before DFA. Um, so let us start. First, what is the Hurst exponent? Basically, since we are in a complex system conference, the important thing to notice is that in complex system with many components, when we consider an aggregated time series, for example, in this case, the Hurst exponent comes from Hurst, that was a British hydrologist that studied the Nile flow, that huge river that crosses most of Africa, and he noticed that the flow was changing in a erratic way or so. And you can think about the flow of the Nile being conditioned by sources, that many sources of this different sizes and so on that throw some of the water. So we have some kind of complex system there, and we have just a single time series. So one of the ways to model those time series that have long memory, they have some kind of persistence, they are autocorrelated for long periods, is the fractional Brownian motion. And the fractional Brownian motion is governed by a single exponent, that is the Hurst exponent. Um, Hurst exponent introduced the concept in 1951, and in 1994, Peng from Stanley's group in Boston, and also with Stan, Gene is one of the co-authors. They introduced the detrended fluctuation analysis in order to estimate the Hurst exponent of a given time series. In that case, that group works with biophysical signals. And the important thing to know, to understand about the method is that the trending fluctuation analysis, basically, we take some time series, we integrate, that basically means that we take the sum of all elements until that point, and then we detrend it. And detrend it means what? Means that we go to the fluctuation function and you remove some kind of local trend. So a local trend can be simply a straight line, for example, or a parabola, a degree two polynomial, and we remove that and we only look into the residuals. Okay, so in this case we are looking into the square of the residuals, and we take the square root. So basically the norm of n2 of this the residuals. And if we consider all those windows with a given scale, with a given size, if you want to, the idea is that if you take the average will be proportional to the scale that we are considering uh, up to a given exponent h, that is the Hurst exponent. Okay, This method is used in lots of fields. Those are some of those that are used. Econophysics, I have used in econophysics, geophysics. As I've told you, originally it was used in biophysics, but in lots of other places where series that have those profiles appear. The method has been introduced in 1994, and since then there were some extensions to the method. One of them is DMA, by Anna Carbone in 2004. Basically, the Detrended fluctuation is a moving average. Then what we can do, if you remember the fluctuation function, there was the sum of the squares and the square root. Basically, you can think about that, and to generalize, instead of using q equal to 2, we can take any q. And in that case, we are looking into the multifractal structure of the distribution. So this is multifractal detrended fluctuation analysis. In 2008, Pobodny, also with Gene Stanley, introduced the detrended cross-correlation analysis. And basically, if you put a 2 here, basically you have the product of two residuals, and you can multiply for 2 different time series, and you can consider that as some kind of covariance. And from covariance and dividing by all the components of the variance, you have the cross correlation. So basically, that is what you can have. And in this case, it's interesting because you can have a mix match of all the previous. So there are, depending on the problem that you are studying, some of those methods are used. Okay. So my concern here is also with methods, but also with the code that can be used. So in terms of implementation, the original computational implementation is from the Boston group that provided a C implementation that should be around 2001, where basically it considered a given time series as input, and the output was just the average fluctuation function. And the idea was that the user was supposed to evaluate the exponent from that time series. And you can ask why, because in order to evaluate the fluctuation function, you already need to apply the least squares to, for example, to fit a straight line or so. Why not to do it? One possible reason is that as any fitting criteria, you can apply the algorithm and it will give you some result. The idea is that the usual thing is this significant or not? Is this meaningful? Well, so, but that was the original implementation. The code in C was and still is available from this URL that you can see here. And since around the early 2000s, we have starting to see some implementations, or at least some subsets of those implementations appears in GitHub in different languages, R, Python, Octave, or in CRAN, in the case of R packages, okay? What are the challenges? In terms of the original formulation, one of the problems is, since we are fitting an exponent, what are the scales that we should consider? Because we notice, and there are lots of literature that talks about some some cases where you have some crossovers, basically 2 scales. For one range you see one scale, and for the other you see the other. What should be the Hurst exponent? And also what should be the kind of statistics that we are considering. And that is the point. Should we consider just non-overlapping windows, or usually sometimes we start from the start and do non-overlapping windows, and then we go until the upper wall and reflect and come with another statistics? Or as Stanley, in lots of papers about Stanley shows us to use the maximum or overlapping. So it considers windows of all sides with that scale, okay? And it considers them all. Of course, we know that there is some autocorrelations, but the statistics are better because there are more samples, okay? In terms of the implementation, of the real implementation in the computer, we want it to be numerically stable, computationally efficient. We want also to ensure that algorithm is doing what it does, okay? And since this is a stochastic problem, we want to generate syntactic time series and to apply the method therein to see if it is giving the right results. So XDFA intends to address some of those issues. The idea is to use the numerical, stable, efficient, and the fast, very fast library to compute all of those techniques that you saw before, and following at the same time the best practices of scientific computing, okay? Ensuring for example, unit testing, basically to test that every function does what it tells that it does, okay? And in different languages if possible. So in terms of history, the original code was developed, taken from the Physionet code available, because the license allows me to do that, and I would like to thank to Stanley Group because of that. And there is just a small change, that is how we use the linear least squared methods. Okay, the original code used numerical recipes. In our case, we used the GNU scientific library in order to do that. So what is the specification? We want to create an interface that can be used either in command line and also from the scripting languages. And in order to show you how we are doing, I will show you, for example, from Python. From Python, you can simply say from XDFA import DFA. So we are applying DFA in that case. That DFA is a sub-package. It has some functions. The most used are the fluctuation functions, because that is most important. H, that is the Hurst exponent, and also the sliding window Hurst exponent, basically where we apply just to a subset and we slide the window and repeat the calculations for different. The advantage, we do this and not, you don't do for each time series, because we can take advantage of the calculations that we already have done in order to improve the speed, and that's the point. Common options, for example, what should be the detrending order of the polynomial? Default is 2. Is the time series integrated or not? For financial time series, the answer is yes. For all the other time series, the answer is no. What are the scales that we are interested in? In this case, all scales. What should be the minimum and the maximum scale? And are we using maximal or minimum statistics? Okay. In terms of, in this case, I'm using Python to import the DFA, and also this example is best run from Jupyter, from an interface, just like a notebook. And notice that basically we are here simply applying, we have a given time series, and we, in order to compute the Hurst exponent, we simply do DFA of age. And the same, we can also place age of t, so the sliding window version, and we apply the DFA and we can simply plot it. It's a lot easier to do that way. So when you output the results in Jupyter, it will show the results just like this in a table. And for example, assume that, so you have also the sliding window version. And in a practical example, I'm applying to some financial markets, to Euronext for indices. And I want to see if the scaling is real as it should, okay? So notice that, as you can see here, and that is quite interesting, it shows that in this case, it makes sense to apply DFA, because notice that in log scale, this is really a power law, okay? The advantage in this case of using DFA, XDFA, is just to show that you can use in very single lines to repeat the calculations. And finally, we are going, the version 1 will be released quite soon. I've been working in it for a long time, but there is also a version 2 working in Works, in this case using C++, using some other features like missing values that you see in real data and so on, and with an easier integration with the script language. Thank you.
All right. So the floor is open for questions. You can unmute yourself or type it in the chat. We have a couple of minutes before the next speaker. You may have the next speaker starting to get ready to share. Is there any question? So I may ask slightly different. So you're applying this to financial series and economic data, but time series they should have some universality across different systems. So for example, if let's say you're familiar with like punctuated equilibrium, like in biology, like you could get data for different species when they, like the Cambrian explosion and others, like is that applicable to analyze other systems?
The idea was is that you should expect more or less the 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 idea in the most honestly what people do in practice is basically they apply the method and they try to see if it explains the data. We don't have any phenomenological model behind. Okay, I'm just saying that sometimes for some of those time series people start to use them, and then in order to compare the results they apply the same method and they discuss it. So yes, it is possible, but the idea is again to see if the results make sense, because as I've told you, it's easier to get an Hurst exponent, but the question is it meaningful?
Yeah.
Yeah. So
Okay, and there is one question, and meanwhile we could switch to the next presentation. Is from Fred Hazelman. Will take sample rate into account, important for physiological systems? So.
No, usually there are some literature, honestly, on biophysical signals. Honestly, most of my applications have been both in financial and geophysical equations, where in most cases, for example, if you are using geophysical systems, the day it's a natural unit, okay? So honestly, I'm not sure how to answer if you consider the sample. I would expect that the results shouldn't depend too much on the scale that you are using. But honestly, this is a guess on my part.
Okay, thank you very much again. And we're ready for the next speaker, Dimitrios Tsiotas. And if you can please share your presentation.
Hello to everybody. Just give me a minute, please, to share the screen.
Yeah, you could share like the PowerPoint or the presentation. Yeah, okay, it's working.
So, does it work?
Yes.
So, thank you once more. My name is Dimitrios Tsiotas. I am a member of the Laboratory of Complex Systems in the Department of Physics, International Hellenic University. And I'm going to present you a work written by Dimitrios Tsiotas and Lykourgos Magafas entitled Structural Analysis of Semiconductor Amorphous Hydrogenated Silicon Carbide Thin Film Alloys based on statistical physics. As you can see in this slide, there the table of contents. Of course, we start by the use of, let me abbreviate it as a-SiC hydrogen thin film alloys. The use of these thin film alloys in PIN photovoltaic components has widely attracted the research interest, especially towards the direction of optimizing the optoelectronic attributes of these alloys that aim to the exploitation of a wider range spectrum. A major effort towards this direction is the increase of carbon concentration in the amorphous hydrogenated silicon carbide thin film alloys, which causes a consequent increase of their optical energy band gap up to the critical ceiling value, while afterwards the energy band gap decreases. However, the increase of carbon concentration induces to the alloys disordering, that it is related to subsequent downgrade of their optoelectronic attributes. Therefore, another direction for the photovoltaic performance optimization. It regards the control. Excuse me, I'm in the previous slide. So it regards the control of the hydrogen concentration of this thin film alloys composition.
Is
Promoting the multidisciplinary demand of modern material physics, our work broadens the conceptualization of complex network analysis of time series by applying the visibility graph algorithm, which is a broadly used algorithm to the energy, let me see, the activation energy data instead of time series data, in order, of course, to study the performance of a-SiC hydrogen thin film alloys as a function of temperature on the one hand, and on the other hand, of hydrogen flow. Our work proposes a framework of dealing with complexity under the state of insufficient where traditional methods of statistical physics are of marginal functionality. As you can see in this slide, we apply techniques. Our proposed methodological framework is composed by a multi-level analysis that consists of 3 steps. Step is based on statistical inference analysis. The second one on pattern recognition, and the final one on network analysis, which employs the visibility graph algorithm that it is proposed by La Casa and their partner and his partners. Prior presenting the methodology, I should the dependence, excuse me, of structural, optical, and electrical properties of these thin films, which are deposited, yes, by using the RF sputtering process on the substrate temperature for different hydrogen flow rates in order to gain the optimum material quality. The available data of the study regard measurements of the DC aviation energy, as I previously told, which were extracted from 4 distinct temperatures that were calibrated at a temperature range from 30 up to 30 and 20 degrees centigrade, and hydrogen flows ranging from 0 to 20 standard cubic centimeters. The characterization of the thin film alloys were based on and heterojunctions, and was conducted by using measurements of current bias voltage, IV, in different temperatures, differential capacitance bias voltage, and spectral response measurement. As you can see in this slide, the available data on which we applied our analysis. They are separated, they are grouped, organized in temperature and temperature range and hydrogen flows. We have 4 stages status of hydrogen flow: 0 SCCM, 9, 14, and 20 SCCM. Each one refers to a single point illustration. And on the other hand, the temperature, it is, as previously told, calibrated from 30 degrees centigrade up to 320, excuse me, degrees centigrade. So, in terms of data analysis, the available experimental data are insufficient because there are not that many, but the multi-level consideration that we apply tries to overcome this restriction. The network analysis is based on the natural visibility graph algorithm, which is an algorithm that transposes or converts a time series into a graph, a complex networks. The criterion that it is applied, it is the visibility criterion, which practically considers the time series as a landscape. It is like an observer standing on the top of a hill, as the example shows, and we develop a connection whether no other intermediate point in the time series intersects the visibility line that it is produced between a pair of time series points. I am not sure if the cursor is visible. Can you see some comments, some points? Is the arrow visible? Okay, thank you. So by applying this transformation, we can convert a time series into a visibility graph. Of course, our approach does not apply this algorithm on time series data. We apply our analysis to data energy, not time series, discrete data, of course, but based on energy semiconductor material, thin film alloys, function of temperature. So practically they are temperature data, and they are grouped in 4 layers, referring each layer to a single hydrogen level. Another method that we used, it is the community detection modularity, the community detection algorithm that it is based on modularity optimization. The concept of this algorithm is that we can divide a graph, a complex network, into communities depending on a criteria of an optimizing criterion, according to which we need our communities to be dense within in their the nodes participating to each community, and sparse, not dense, between the communities. So the statistical inference analysis, as you can see in this slide, reveals that the energy, the activation energy is statistically indifferent to the temperature. Whereas, on the other hand, non-zero hydrogen flows, in that flows, the temperature affects the semiconductor's structure. So in our first approach, we applied statistical inference analysis on energy data, activation energy data, expressed as a function of temperature. On the same step, in the same step, we computed a 95% confidence interval on the average and maximum values of a-SiC hydrogenated thin the data of activation energy in order to examine if these activation energy values are statistically different among different levels of hydrogen flows. Of course, the major observation is that we found a statistical significance difference between the zero level, the non-zero levels of hydrogen flows. This is one conclusion was that when we apply hydrogen flows, we get better structures of this component. As a second, on the second part of the analysis, we applied pattern recognition based on curve fitting methods. Also, this approach was applied on activation energy data. As you can see, all fittings that are associated to non-zero hydrogen flow levels shape convex shape patterns that implies that there is a global maximum that can be found in each curve. That means, of course, that there is an optimum temperature value where the activation energy it reaches the maximum, the optimal values. That means that we can get optimum structures. Also, parametric fitting was applied to activation energy also data, but in this time they are expressed as not as a temperature, but as a hydrogen flow function. As you can see, the Gaussian and quadratic curve fittings presented the highest coefficients of determination that expresses that there is most likely the activation energy to also have a convex shape. That means that we also can reach a global an optima in this curve, regardless the insufficient number of cases. So with this approach, we can observe that in higher hydrogen flow levels than 20 SCCM, it is most likely to have lower values than the activation energy that was observed by the curve fitting as optimum values. So higher hydrogen flow levels are probably described by worse structures than this one achieved by the experimental measurements. Also,
Dimitrios, I'm sorry, but yeah, your time is up. Can you
I'll go faster. Okay. We applied another curve fitting approach, but this time on maximum temperature levels and hydrogen levels. And the network analysis allowed us to detect, to apply a multi-layer approach that let us find that there was a rich club configuration and the temperature range from 120 up to 180 degrees centigrade at the distinct DC activation energy sets that corresponds to a different structural behaviors of our thin film alloys. The overall analysis show provided insights about dealing with activation energy and structure structural analysis within the context of insufficient connectivity. We propose this approach for further applications, and thank you very much. Hope English was good enough to understand. Thank you very much.
Yeah, so yeah, we're a little bit over time. While I'm switching to my presentation, if there is a question, like you could ask, otherwise you could unmute yourself or put it in the chat. If you can stop sharing, I could go ahead and share. Meanwhile,
okay, let me. Okay, I stop share.
Okay,
Thank you very much.
Is there a question? Of course, like we could continue talking, but in the interest of the schedule, I will switch to my presentation, and I hope you can see it. Is that okay? If you don't see it, please let me know. But yeah, I'm starting a little bit later, so we'll go 5 minutes probably over the scheduled time, but we have only one talk after that, so it's okay. All right, thank you for your talks so far. All right, so I'm going to talk about something that has been an interest of mine for a long time, which is self-organization, and that's connected to structure formation in like different systems in general, in systems of any nature. And as you could see here in the picture on the left, you have the cosmic evolution, which I'll talk in the next slides. But based on the data and the models that exist, we have created our model of how the mechanisms of this self-organization, and then compared it to the data from systems of any nature, and applied it in this specific work, which is a paper that we're publishing right now with Springer, to stellar evolution, to just check another system whether it applies. So what is the general idea? So you're all familiar, I'm sure, if you're interested in physics, with Carl Sagan and his cosmic calendar, which studies kind of, from my perspective, the self-organization since the beginning of the universe, and puts that into a 1-year timeline, all 15 billion years. So you could see, I don't have time to go in detail of everything, but the message is that at the beginning, not much is happening for a long time. And at the end, all the self-organization or complexity increase is happening in the last few seconds, our whole human history, at least from our perspective. The other civilizations, they'll have their own calendar, but it should be similarly accelerating like this if this is universal. And also, if Carl Sagan is wrong, here is a list prepared by Ray Kurzweil of 15 sources, Modis and the Encyclopedia Britannica, and also Carl Sagan, of the acceleration of major complexity increasing events happening from the since the Big Bang. And you could see the enormous acceleration as on the vertical axis, you see the time to the next big change in complexity or structure. And the x-axis is the time before present on the log-log scale. And you see that, let's say 10 to the 10 years ago, you had to wait almost 10 to the 10 years for something to change in the universe, something new to happen, like formations of stars, galaxies, chemistry, and so forth. And if you go at the end of this graph, say 10 years ago, you needed to wait 10 years for the next big thing to happen, like, I don't know, internet, cell phones, 5G, like the progress of self-organization. All right, so and Eric Chaisson put this beautifully in this poster for cosmic cosmic self-organization, pretty much from our perspective, where you have increase and acceleration, which is not the point on this graph, but on the next ones, where you have increase of the size of them, starting from particles, atoms, molecules, cells, organisms, ecosystems, society, and whatever comes into the future. And now he works at Harvard, but when he created this poster, his office was next to my at Tufts University, where I was at the time. And another exponential measurement is, as you well know, by Ray Kurzweil on calculations for CPUs, calculations per second, where he goes even to, because it's per $1,000, to find even a super exponential growth, like a double exponential. But if you just look at the physical side, we think it's exponential. Also, this is, so what is the quantity quality or the size complexity relation? If you go to a paper which is titled by Size Complexity by Bonner in 2004, he collects data from different systems, and he says that size increase requires an increase in complexity. So you cannot build a bigger system without structure increase as a measure of its complexity. And here is from Martin Willensdorfer candidacy exam summary that for biology, larger organisms are more likely to evolve specialized cells. So you need the size to get greater complexity, and we'll see some graphs shortly. But also, once you have these specialized cells, they promote size increase, because now you could form different organs in biological systems. You could think of cities or society also in similar terms, right? So this should be universal across all systems. Corollary from, or the economy, right? And the corollary, the data, only few large and simple organisms exist, and only a few small and complex systems, right, are found. So if we look at a similar example, but for a social system, this is from anthropologist Carneiro, published in 1967. So what he did is he went to the Amazon rainforest, which at the time probably was much more preserved. And what he was trying to do is to look for isolated societies, he called them autonomous villages, and to count the number of organizational traits as a measure of their differentiation and complexity, similar to biological organisms, as a function of their size on the x-axis. This is a log-log plot. And you could see very clearly that all of his villages lined up around this line of best fit, which is a power law here on the lower left corner. And as it was said on the previous slide about biological systems, no small and complex societies exist, and no big and simple societies exist in his data set, which means that to form structure, you need increase in number of people, and to be able to preserve the structure, you need to be able to keep the number of people, you need to actually create more organizational traits, more institutions. In his case, these villages will have like a chieftain, a priest, a trait structure or something like that, right? But you could extrapolate this curve up to cities and societies to this day. The only word of caution I'll say is that you can't consider countries as isolated systems like he did here, because they connected to all other countries, and small and complex countries exist, like, for example, Singapore, which is very small but very highly developed and organized. On the other side, you have much larger countries that are not, but they are part of the whole system. So to do a fair comparison, basically, you have to find another set of civilizations and compare them, which we are not there yet. Maybe we'll do, as Carl Sagan was hoping. He was right that there are extrasolar planets. So the conclusions that Carneiro did for society is that what is it that the numerical increase can bring qualitative structural or complexity transformation in social structure? The answer is population, which is size. So you see, size is needed to increase complexity. And the increase of sheer number of persons in society, when that increase exceeds certain threshold, gives rise to new forms of organization. So the message is, if the complexity of our society is to keep increasing, which means new technologies, new forms of transportation, new forms of organization, which benefit every single person, to increase, the number of people should increase, which of course poses questions from sustainability, and maybe we need to go in outer space, but we need to keep increasing the number of people, otherwise the level of complexity increase and development will stop. And he found that the evolutionists struggle to increase structure in proportion to size. So stop the number of people increase, stop the development of human society. And here are a few examples from different sources. This is for CPUs. You could say this is efficiency or complexity versus size of CPUs, a power law. Population size predicts the technology complexity in Oceania. This techno traits per tool as a function of the size in Oceania. Power law, number of cell types, as we discussed in organisms, as a function of number of cells. A power law, number of castes in ant colonies and the number of ants in the colony. A power law from Turchin, we have the hierarchical levels of societies as a function of their change in population through time. A power law. And also in Indian states, the number, these are the stars of the states, and the number of occupations, different occupations, like Carneiro's work on different organizational traits, as a function of the population of the state, almost the same curve, power law. So you see this universality, and the last curve is even more informative because you have the increase of complexity of society as a, let's say, measured as GDP per person, where you could buy more things or create more technologies as a function of the population of the world, and you see that they're almost overlapping, right? So everybody gets better, everybody gets richer if there are more people in the world. Again, we have limits on this planet, but we should keep this in mind, not to say, oh, we need to stop population growth forever, because in that case, these curves will go together and stop, and will not get anything more interesting in our society. We'll freeze, let's say, in the past, let's say people were in Middle Ages for 1,000 years. We don't want that to repeat. Okay. So here is our model. We look at the different characteristics of any complex system. This is for CPUs from our previous paper that we published, but here we have the, and Hegel talked about quality and quantity a lot, quality-quantity transition, which is the same as size complexity. So people have noticed this everywhere through history. You could go even to ancient Greece and read about those. Like the whole is bigger than the sum of its parts. It's quality-quantity transition or size complexity. And if you put those in a positive feedback loop, where to, as Carneiro said, to increase the size of society, you need to have more structure, and to have more structure, you need to increase the size. That's a quality quantity. And if you model this the usual way of positive feedback with the rates of increase of each of those as a function of all the others in the loop, you get numerical solutions of strictly exponential growth. You get this analytical solutions, strictly exponential outcomes of positive feedback, and you get between them the power law relations. So these power law relations are indicative that if you find them in nature, they fit in this model and they will have this exponential growth. And there are other details that I don't have time to discuss today. And here is one famous example of the transistor count versus time, which is a strictly exponential based on like this measure and fits the model, and that's the Moore's law. So how does all this relate to stars, or how the stars relate to all this? And which is the topic of this. So this is to confirm or reject that model or hypothesis, to check the model, and also to learn something new about stars if we can. So we consider stars as a complex system, which means what's happening. You have, during the life of the star, nucleosynthesis, as you can see on this picture on the lower left. The nucleosynthesis is just combining of nucleons into heavier nuclei, right, into groups, and we measure the degree of grouping. And of course, this degree of grouping, the more they group, the less the baryonic or the particle entropy, right, because now they have less degrees of freedom. Of course, as you can see on the picture on the right, you have so much radiation that you more than enough to increase the entropy in the outside world, in the universe, that you always obey the second law of thermodynamics. But we're interested what is happening inside the star. So this degree of grouping is a measure of complexity, or one of the measures that we propose. You could have like layered structures inside the stars, or magnetic field, some other measures that you could come up with. And here shortly is just that we look at this. A is the atomic number, beta is the number of nucleons of each isotope. And those data that we get from study of simulation, of a simulation done by Nomoto in Japan. And that simulation matches the Saga database, which are observations of isotope abundances in exploded stars, in nebulae, to make sure that they correspond to reality, right? And he kind of calculates the number of isotopes as a function of the size of the star. And here we're using their data to calculate, and a student of mine did these calculations to measure the amount of grouping. Here it's normalized by beta, which is the initial number of nucleons in the star, to be relative to each size. And here are the results. So I'm almost done. So the results are the following. The progress of nucleosynthesis, which is like the measure of structure or complexity or entropy decrease, as a function of the size of the star as a total number of solar masses, you could see power law trends. And what's the difference between these different lines is just the initial metallicity. So circle is like primordial star, which will have zero initial metallicity. And in astronomy, metallicity is how much initially they were grouped. For example, if another star exploded, it would have already synthesized some heavier elements. So the metallicity is anything heavier than helium. And if it is zero, it is just initial primordial star, which there are not many today for obvious reasons. They have all exploded. And then there are heavier stars that are second and third generation formed with more heavy elements initially. And first, you observe that these curves, their slope increases, and they reach higher level of complexity. They started from the second and third generation stars. It seems like the processes are going faster of self-organization. And also you see the dependence on the mass of the star. Not only that, you see that the rate of nucleosynthesis, as noticed in this acceleration of self-organization in the universe, is dependent on the size of the star. So not only you have increased complexity with size for stars, but you have increased rate of achieving that complexity as normalized per the size of the star as a function of the size. So if you go back to societies, the larger the societies, the more number of people, the faster they develop, right? The faster the structure increases, the better it is for everybody. You get new technologies, you get new medical advances, you get everything just by increasing the sheer number of people. again, with the caveat that we have to think about the environment. If we did everything sustainably, then we could achieve larger increase without harming the global warming, the environment. Here is the flow, which is the number of nucleon additions per second as a function of mass of the star. Again, power law curves, and this is the kind of action efficiency, the energy and time per one nucleon addition. So whatever we look at, whatever we measure, you could go ahead, measure, I don't know, information measures, entropy. We predict that they'll fit here. And also based on this, because it fits into the model that I showed you, we predict that if somebody calculated the rate of increase of these nucleon additions or nucleosynthesis during the lifetime of the star, it's going to be an exponential curve. We don't have this data to do that, but that's another prediction or feature of the model. So I'll stop here, and that we conclude the stellar evolution, at least with the data that we have, obeys this size complexity rule. The larger the star, the more complexity it has at the end of its life, and the faster it does it. And it matches the observations in nature and biology and society. And the characteristics that we have looked at specifically as measure of complexity, as the grouping of elements, the number of nucleons addition per unit time, the flow of these events, also increase power as a power law. So not only the size complexity, but the rate complexity, the flow complexity, there are more things in the model that we could check than just the size complexity are also obeyed. And so this size complexity rule is only one part of the model, right? And it's observed by other people everywhere, but I'm out of time, so I'll stop here. And I'll thank you for your attention. And if you have some questions, I'll be happy to answer one or two now and more later. You could always feel free to contact me or email me if you have interest in any of this or collaborating. So are there any questions for me at this point? You could either unmute yourself or you could type in the chat. All right, thank you. Or you could email me later if you have some. And if you don't, we could move to the last speaker in the session. And that is Alexander Boyd, who will talk about thermodynamic machine learning to maximum work production. So he's information physicist that he got his PhD at UC Davis and James Crutchfield. So let me, I think, am I still sharing or I stop sharing? Oh no, I have to stop sharing. Okay, so here is Alex Boyd's title, and the floor is yours.
Thank you. Can you hear me?
Yes.
And you can see my slides?
Yes.
Great. Well, thank you for the introduction, and thank you everyone for attending. Today I'll be talking about a collaboration between me, Jim Crutchfield, and Lykourgos on, as mentioned before, the thermodynamic machine learning through maximum work production. So I am indeed a information physicist. So when I think about machine learning, I think about the thermodynamics of intelligent agents, which I would say started with Maxwell's infamous demon over 150 years ago. Can you see my cursor, by the way?
Yes.
Good. So Maxwell's demon was a thought experiment proposed by James Clerk Maxwell, where he said that an intelligent and neat-fingered being could be placed in a physical system. And by observing that physical system, say a box of gas with a partition in it, could do something rather interesting. He said, okay, let's say the demon has control of a frictionless door, and it can observe when a particle is moving rapidly from right to left, and open the door without doing any work to let that particle through. And when a particle is moving slowly from left to right, it could open the door again to let the particle through. And what would happen through that process of the demon intelligently manipulating its environment is that the box of gas would spontaneously organize into a bunch of fast-moving particles on the left and a bunch of slow-moving particles on the right, which would mean you'd have a hot gas next to a cold gas, which would be a temperature difference. And that means that you could attach a heat engine to it and use that temperature difference to produce useful work, which would seem to violate the second law of thermodynamics. It was seen as a paradox for some time. But what we recognize now is that this process has some cost that's associated with what's happening inside the demon's mind, with the information contained inside the demon. So the more modern picture is a little bit more nuanced here. Rather than just moving disordered heat energy and turning it into ordered work energy, say by raising a mass, we recognize that we have another thermodynamic resource, an information reservoir, here represented by a hard drive. And by randomizing that hard drive, you can guarantee that the second law of thermodynamics is preserved by essentially porting all the information contained in the heat into the hard drive and all the useful energy into work. Now, as I said, this still satisfies the second law of thermodynamics, and that implies some bounds. Specifically, it implies a bound on how effectively the intelligent agent can harvest energy. This is known as Landauer's bound. A work production is bounded by kBT, which is the energy scale of the thermal reservoir. So T is the temperature of the reservoir. It's bounded by kBT times the change in Shannon entropy of the hard drive measured in nats. So here's the Shannon entropy of the hard drive initially. Here's the Shannon entropy of the hard drive finally. So, my slides, there we go. Just had a problem with my slides. So this work production depends explicitly on what's inside the hard drive. So because of this dependence on the initial uncertainty of the hard drive. So for instance, the hard drive could contain just random noise, in which case you can't extract much work. Maxwell's demon couldn't extract much work in this case. On the other hand, it could be all zeros. It could be a totally erased hard drive, in which case you can produce a lot of work, because basically your only contribution is this positive term to the bound on work production. Alternatively, it could be something totally predictable, say the compiled works of Harry Potter, but it would be very complex and difficult to extract the work. So you can extract it, it's just you have to create a complex and intelligent agent to harvest it. So practically, what might we do with this hard drive? Let's say we don't actually know what's on the hard drive. And so we treat it as a black box. It's our informational environment. And what we would do is we would say, take some data from it to determine what's on the inside, to sort of peek into the structure of the box. So this is sort of the framework that we have laid out here. Specifically, we have a black box information reservoir, and we take some length L time series from it, where each bit is output at intervals of length tau, or of time tau. And then you also have a bunch of different candidate daemons or agents, thermodynamic agents, each with their own internal model of what's going on inside the box. So one daemon might say, oh, I'm pretty sure that inside this box is just a bunch of zeros. It's going to be all zeros. And another daemon might say, I'm pretty sure there's Harry Potter inside of this box. And these models are characterized by a parameter, theta, in this case. Theta will essentially be some parameter that dictates the estimated distribution the agent predicts about the internals of the box. And based on that estimated distribution, based on that theta, the agent will interact with copies of the string. And in doing so, harvest different amounts of work. So the same input string, input to models with different, the same input string, input to agents with different models of that data will produce different amounts of work. And what we do then is we select the maximum work agent. So this is a training process where we determine essentially what is the thermodynamically best model theta of the data that we've taken from the box. And this is what we call thermodynamic learning. Learning that's motivated by intelligent work harvesting. So if we want to understand what happens through the process of thermodynamic learning, we need to understand how an agent harvests energy. And while I don't have the time to go through the full details of it, I think I can give you sort of a sense of the general idea. And the general idea is that the agent, say, takes this time series one bit at a time. And we look at this interaction where the daemon harvests energy from a single input symbol. And say this input symbol realizes either an up state or a down state. And going back to Landauer's bound, we might say, oh, well, we know based on Landauer's bound that the maximum work production we can get out of this on average is the change in entropy going from the initial state to the final state. So in this case, going from 80% up, 20% down to 40% up to 60% down. But that only tells us on average, on ensemble average, how much energy we harvest. And instead, we need to know specifically how much energy we harvest if you realize just the up state or just the down state, and then output just the up state or just the down state. And for that, we have to go into the mechanism of how you efficiently harvest energy. And to do that, there's a pretty general mechanism that allows you to efficiently manipulate data, in which you start by, so we have here these blue bars measure the probability mass. The black lines here represent the energy of each state. You can instantaneously change the energy levels to be in equilibrium with the estimated distribution. And then very slowly, quasi-statically, change those energy levels, allowing probability mass to flow and stay in equilibrium until you reach the final distribution. Now this process, because it's quasi-static, doesn't dissipate any energy. And if designed correctly, always produces or requires zero work. And then you instantaneously change to your default energy landscape. So this is a cycle where you've updated your distribution. And what you find is that you can associate work production with every particular state trajectory based off of this sort of protocol. So for instance, if you know that you started in the up state, when you make the transition to this energy landscape, you've invested kBT log of 0.8 in order to transition into the equilibrium distribution. So what you find then is that for every input-output pair, you have a particular amount of work invested. And in general, you find that if you have some model theta of your data, and you make and you design your agent to be perfectly efficient for that model, and you make a transition from an initial state to a final state, the work required to do that is KBT times the log ratio of the input probability over the output probability. Now, I've shown you sort of a candidate way to achieve something like this, but this is a fairly general result that comes from Crookes fluctuation theorem. And if you want to see a derivation of it, we have a paper on arXiv. And this essentially describes the general principle behind harvesting energy from finite work. And it can be generalized to complex agents. So there in the previous slide, I showed a single system that was processing a single bit, but you can add complexity to the system, add complexity, hidden states to the agent, such that it can efficiently harvest energy from any input distribution. And what you find then is that if you maximize the work production, assuming a particular input distribution dictated by your model theta, and you receive a particular input string or a word y0 to L, the associated work production is KBT times the log probability of that word given your model, plus a constant term, which is essentially the benefit of randomizing L of the symbols. And it turns out that this can be expressed as KBT times the log likelihood of theta given your data. So maximizing the log likelihood of the model from data also maximizes work production. This is kind of cool because it directly ties information thermodynamics to machine learning. So in machine learning, you have some data here. And that's sort of your substrate. And then in information thermodynamics, you have physical systems as your substrate, which encode data. Then in machine learning, you have models, which assign probabilities to your substrate, to your data. They operate on the substrate. And then in parallel, you have in information thermodynamics, you have controllers, which manipulate the substrate, the physical system that contains the data. And then finally, in machine learning, the log likelihood is treated as a performance measure of the model on the data. So how effectively your model captures the data is given by this log likelihood. And then in information thermodynamics, work is a natural performance measure. And we find that the work production of the agent on the data contained by a physical system increases linearly with the log likelihood, the same performance measure as machine learning. So what this tells us is that work production is a thermodynamic performance measure for learning, specifically for the process of parametric density estimation. If we carry out the thermodynamic learning process I showed you in the beginning, we're essentially doing machine learning in the technical sense. So stepping back a little bit, what does this suggest about the world? I think many of us are familiar with the picture of the lifetime of the universe, where there seems to be a trend towards increasing complexity intelligence, starting from simple biomolecules, turning into living single cellular organisms, and then complex multicellular organisms, and then complex superorganisms composed of many multicellular organisms. It seems as if complexity and intelligence are increasing. Should we expect that there's some underlying thermodynamic reason for this? Is there a reason that physical systems naturally learn? Well, this question becomes very close to the question, should we expect work production to be maximized in nature? So we've seen hints of this. I think one example is Prigoghine's principle of minimum entropy production. It also addressed by people like Onsager, Kirchhoff's law. But these Jaynes also has investigated minimum entropy production principles. These are very similar to maximum work production, but they only apply in limited cases, and you can find counterexamples. So I would argue that there isn't yet a conclusive reason to believe either of these is true about the universe. But I would say that at least the result we have here indicates that if one is true, the other is true. We have an equivalence between maximizing work production and natural learning. So with that, I'd like to thank my collaborators as well as my funding sources. So yeah, that's it.
Thank you very much. Any questions for the last talk? So I have a question. If somebody else has, please type it. So if you think about fundamentally the least action principle, right? So everything tends to occur with the least expenditure of action, which is most general, like the product of energy and time, or the integral over the Lagrangian. And then you say, okay, I have to always, or nature always obeys this principle as minimizes action for any process that occurs. So now when you put things, like you showed in the last slide, the scale into getting larger systems, which connects to my talk, I think, a little bit. And then you get more complex organisms, and then you try to minimize or to obey nature that minimizes action for each event in the system, being it computation or chemical reaction, metabolic reaction, information transmission in society. Do you think we could say, or maybe we could talk more about that later, that this drive, physical drive towards that action minimization may actually lead to force that structure to form, or lead to structures that minimize action for one event, whatever event is in the system, that being a thermodynamic event or information or whatever event. So I don't expect that we could make some broad conclusion now, but I would be interested to know what you think about that, or in general.
That's an interesting point. Honestly, I hadn't thought about the minimum action principle in terms of this yet. It definitely seems intuitively connected. I suppose my first thought is, the minimum action principle is about selecting time trajectories, right? And a lot of this work is based off of detailed fluctuation theorems, which are derived by people like Gavin Crooks and Chris Jarzynski. And I think that might be a connecting point where you could formalize the relationship between the minimum action principle, because those detailed fluctuation theorems directly relate the probability of a trajectory to its entropy production, right? So that's sort of one of the most revolutionary pieces of modern thermodynamics, is now we have, rather than the second law of thermodynamics as an inequality, we have equalities, right? That state explicitly how much entropy you can expect based on the probability of a forward trajectory versus its reverse trajectory. So I'd say it's an interesting area to explore, but I don't have anything concrete to offer you.
I know, yeah, but I'll be happy if, say, later, or when you talk to Lykourgos or Crutchfield, if you get some ideas, I'll be happy to have more interaction about that.
Yeah, that would be interesting.
Any other questions? And also, this reminds me of thing that is called a thermal diode, which is supposed to pass heat into one direction. So it looks like your Maxwell demon, at least superficially. I don't know if you can make any connection to these thermal diodes, like they are like one-way transmission of heat. And actually, surprisingly, people started even, I think, using them to heating houses or something like that, where you could pass heat one way into the house. Let's say make a window of a thermal diode, and the heat goes one way but not the other, which is very looks like it will decrease the entropy, right?
I admit to being a little bit ignorant on this topic. So thermal diode requires no energy to operate. It transports heat passively.
Yeah, I'm not exactly sure about the microscopic way it works, but I know that people have been actually using it practically to transmit heat into one direction, which is really mind-boggling. But the first attempts have been in the 30s, and most recently in 2015 there was in Nature Nanotechnology like results of this diode. So it has been an interesting area of development, but that may be related to what you're doing, or maybe not with the Maxwell demon. Okay, so I get from Damas, right, that you could use stochastic least action principle. I guess that's out of the number of trajectories to, like in quantum mechanics, right, to have to pick the ones that the most probable or the shortest, but they are not the only ones, like in classical mechanics, right? Yeah. All right, so if there are other comments, let us know, or any questions for anybody else during this session. And if not, I could thank again to all of the speakers and to Argyris for kind of starting the Zoom session. And let's have a round of applause for everybody who talked today. And I thank you. With this session concludes, and we could go to the main program. Thank you, everybody. See you.
Bye. Good night,
Bye.
everybody.